And we are live. So, welcome to Cpp.chat, the latest podcast for C++ developers by C++ developers. Before we continue, I'd like my fellow host, John, to read this week's disclaimer.
Thanks, Phil. Disclaimer this week. The medical information on our website is provided without any representations or warranties expressed or implied. You must not rely on the information on our website as an alternative to medical advice from your doctor or other professional healthcare providers. Thank you very much. So today we have one new guest who hasn't been on before and two old timers. Ben Craig is a principal software engineer at National Instruments, and this is his first time joining us on this side of the camera. How are you today, Ben?
Doing good.
Have you been watched many of the shows previously?
I have not watched many, but I've listened to many on my drive to and from work.
So you kind of know what we're about.
More or less.
Okay. Michael Caisse is no stranger to these microphones. Michael was on our very first episode, but he hasn't been back a while. But I think when he got on Cpp.chat like 2 weeks ago, or Cpp.cast a couple of weeks ago, it made him miss us. So, Michael, how are you handling this sudden fame for being on the show with a big audience like that?
To be honest, it was nerve-wracking, which is almost funny. But I kept waiting for Rob to ask me the question that would just like throw me over the edge, and I'd be, "What do I do? What do I say?" What's funny about that, John, is that Rob and Jason are nicer than you are, John. And so this is the forum in which I'm going to get the question I can't answer.
That's right.
Oh yeah.
John's going to figure out what's going to wind you up and get you saying, "We don't need no papers. We don't need no stinking papers." So another individual who is no stranger to the show but hasn't been on for a while is Odin Holmes. Odin, you haven't been on under this format, have you?
Nope. First time with Phil, so we'll see how different it is.
All right. Well, Phil, he's this cruel slave master.
Oh yeah.
So I'll turn it over to you, Phil. What are we going to talk about today?
Well, before we get to the main topic, we have a few bits of news to get through. As usual, we have some conference-related announcements. So Pacific++, their tickets are still open. The speakers have now been announced. I believe they're all on the website. So if you're in that region thinking of going, have a look there. I'm sure it's going to be a really great conference. For CPPCon, I'm going to hand back to John, who's going to be a bit best qualified to talk about that, I think. John?
Right. So we haven't made a big announcement about this, but once we figure out who all the speakers are, one of the things that we want to do is we want to publish the schedule for the conference as soon as possible. But that takes a long time. There's an awful lot of variables, and as you can imagine, scheduling constraints. But one of the things that we have to do is we have to send back to all the speakers a list of all the other sessions, so they can tell us, schedule me before this session or after this session or not opposite this session. And so that list, if you would like to know all the sessions that you're going to see at CPPCon, and I have to say, we don't mean all because there are a lot of things that get scheduled at the last minute. It's that kind of conference. But if you want to see the bulk of the conference, those are actually online. We have not published them. You won't find a link to it from the website. But if you go to the CPP Lang Slack channel and you go into the CPPCon channel, there is that link has been posted there. And if it has scrolled off, you can ask somebody else for the link. But anyway, it's the list of all of the sessions. And I don't mind saying, I think it's a pretty impressive list of sessions. I think you're going to be pretty excited about what we have. So if you're curious about that, that list is now available.
And if anyone wants to come and see one of my talks and they don't want to miss somebody else's in particular, I will be taking bribes in order to make sure that schedule doesn't happen. Just let me know. So another conference that's coming up, of course, is my one, C++ on C. So we're getting closer to the end of the month now, so anyone thinking about submitting now is really the time to get that. that submission in. We will be closing at the end of the month. And then meeting C++. Their schedule's not up yet, I think, but the speakers have been notified. So that program is in process. Meeting C++, of course, another great conference. Will be another good one this year. And then one final piece of news I've just slipped in, just abusing my position here. Oh, yeah.
Oh, I was just going to mention about meeting C++. For those who are interested in embedded, there's a embedded pre-conference day for meeting C++ this year. It's an experiment for him. It's his first time doing that.
Very relevant to our topic today. So I don't know how I missed that one. Or pointed out. So yeah, the other piece of news that I wanted to slip in relates to my JetBrains role. So I thought this was going to be interesting to a lot of people. One of our products, ReSharper C++, so the plugin for Visual Studio for C++. Now, as of the latest EAP, that's what we call a beta for 2018.2, should be released the next week or two. Now supports C++ CLI. So some people have not heard of that at all. If you have heard of it, then you'll know that you really want this. If you haven't heard of it, you're probably better off that way, actually. But it's basically the interop language between C# and C++. So given that we cover C# and C++, but we weren't covering C++ CLI, this is a nice one to get covered. So there's actually a blog post that I've just written that's going to go out in the next few days. So maybe I'll put a link to that in the show notes if that gets done in time. So that's the news out of the way. The topic for today is going to be in the sphere of embedded development, which is quite a big topic with quite a lot of different directions we should go in. So we just got a mixed bag of people from within that domain with us, and we're just going to see where it goes. We've got a few talking points possibly. And just to kick it off, I actually want to mention a tweet that I saw today from John Rager, because I thought this would get the discussion rolling. And he said, I think it's 100% clear that the C++ committee should remove Volatile. So who wants to tell us why that's actually relevant to embedded in the first place?
Was this in jest?
Was it what, sorry?
Was this in jest? Was he joking around?
I don't think he was 100% serious, but I don't think he was joking either. I think it was a serious hyperbole, maybe.
I'll tell you what.
Volatile is the one keyword that is the embedded keyword, and so it's like you're taking our one last all the way.
We don't even get to use real C++, and now they're going to take our one thing away from us.
Yeah, the one thing that makes it useful.
Well, if they gave us something better, they could take it. Like they gave us like volatile memory addresses or a more well-defined volatile. I mean, it seems like what volatile means differs considerably between different compilers, especially if they're not the big three.
I think that's one of the issues. So my story is, I was hoping to tell my story. I actually, it's the one paper that I've actually written and submitted to the committee, but before the committee even met, I withdrew it because someone pointed out, well, there's some issues here that we're going to have to think through a little bit. Because I was writing this actually with Dan Sachs. We were writing it together and we submitted it, and then someone raised something and Dan said, yeah, we're going to have to think about that. Let's just withdraw it and put it back in. But what we were trying to do is I was talking with Dan, and he was talking about a trick he used of if you have a read-only port, then he essentially makes it a const object, and then he just calls members on it and reads from it. And what I pointed out is it's in C++, you can't have something that is const that is not initialized. The language requires that. I mean, he was essentially casting it to a const object. So the object never really got initialized. And he was essentially lying to the compiler about what was actually happening. He was doing this cast and saying, well, there's a const object when in fact it's not even an object at all. It's never been constructed. And that all works. But what I pointed out, I said, if the compiler ever has an optimizer that can actually see what you're doing, it can optimize all that away. It's completely undefined behavior. And so what I said is what we should do is we should get the committee to say, if an object is both const and volatile, it does not have to be initialized.
Sorry.
Because that's what we're really trying to say. We're trying to say, because if you have a read-only port, then you don't want to write to it. You want to read only, so you make it const. But if you make something const in C++, it has to be initialized. The compiler has to give it its initial value. And that's exactly what you do not want in this situation. So I wrote this paper up. As I was investigating the paper, I talked to Richard Smith, and he actually asked me to include something else in the paper, which was probably a mistake, because that's kind of what sucked the paper away, because it's like, that's really undefined behavior. But what he told me is, he said, here's the real problem with Volatile. The standard says what Volatile is. And if somebody were to implement a compiler following the rules of Volatile, it wouldn't work. If it's following what the standard says about Volatile, because as you guys just hinted, there are things about Volatile that compiler people just know, this is how it's used, this is what we can and cannot do. That's not in the standard. It's not actually documented. And that's the problem that we have with Volatile is, and I think that may be part of what John Rieger is trying to say, which is that what the standard says about Volatile and the way it's actually used are not exactly the same thing. And if you actually were to figure out what you mean, you're probably going to make certain optimizations that aren't, I mean, there's no way to split it out. And so that's the problem. In fact, one of the, what it was that, Smith had asked me to add to it was to specify a particular case and saying, can I make this optimization on a volatile object? And the problem was, well, you can't read the standard because the standard doesn't really say what it needs to say. You just kind of have to know. There's kind of this non-documented agreement between compiler makers and embedded engineers about what volatile really means.
So beyond just what volatile means there, the biggest usage of volatile that I know of is it involves casting address to like a volatile pointer. And that's just big piles of undefined behavior right there, because you never made an int or whatnot in that location. And there's papers going on right now to try to fix that in other cases using this thing called stood bless that doesn't exist right now. And so, yeah, there's piles of problems already, but the compilers mostly make it work.
Right, but they're not following the standard to do that. What they're following is industry practice that says, if we don't do this, we're going to break a lot of code. So we have to do this, even though it's not really what the standard says.
I believe if you are telling your compiler that you're in a freestanding environment, then a variable with static storage duration, which probably would be that input FIFO buffer or port, does not have to be zero initialized. It's implementation defined.
It doesn't have to be zero initialized, but you have to have made an int somewhere before you point at it. So if you just have
no, sorry, I'm out of order. I'm responding to John's story about the const.
Yeah, but I think
believe
Ben was
that is still conforming.
Okay. But yeah, what you mentioned, yeah, that makes sense to where if you wanted to have a static const volatile and try to throw a few other keywords in there for good measure too, you had one of those, then maybe you don't have to have it. You can assign it a value, but it isn't required to actually have that value.
Well, no, the idea is it's read only, so you don't want to assign it anything. And in fact, that's the problem, is that when you say that it's const, in C++, you make something const. It's got to have an initial value. Syntactically, you can't say, oh, I'm creating a const object at this location and have it. That's what he was doing. He was doing placement new to create an object in a particular location and playing games so that there was never anything that was actually written.
Oh, yeah. So he wasn't like putting it there in the linker script. He was placement newing it. Okay, I get it. Sorry.
He was placement newing it, and nothing would ever get written to the memory, and that was fine because the object's this pointer was pointing to the port that he wanted to read. And he wrote all his member functions to do these. I mean, it was really brilliant. It made it so usable. It improved the usability of the code so much. But what I was telling him is, if the compiler could figure out what you were doing, it can optimize it all the way, because you're You're doing something that's technically undefined behavior. And so I said, we should clean that up. It's an obvious thing. If you have something that's both, that is a port that's read-only, it should be const and it should be volatile. And in C++, a const object has to be initialized, which is the opposite of what you want for a read-only. So
some people are posting other parts of the Twitter thread that John Rager was involved in. And there was one comment that was worth getting your opinions on, because he said that, paraphrasing it, that there's actually not much benefit in Volatile as opposed to function calls. What's the opinion on that?
Well, maybe I won't be able to qualify stuff with atomic or restrict either. For all those C member functions.
Yeah, I'm not sure what I'd actually ever use that. I mean, I guess I probably don't code in the same way most people do in sort of that context, because
we may have a show title.
I wasn't going to tell you that.
Well, I mean, the only thing that's really, if you're talking to hardware registers, then that's not cross-platform or cross-chips anyway, right? So you're locked into that architecture, that specific chip model, if you're talking to special function registers, which are, the volatile part of your program for the most part, unless you're trying to model atomics or something. And at that point, why not just do inline assembler? Because then all the different compilers that support that will agree. And so, you make some function, maybe you make a class the same way you were talking about, John, and then just have all the member functions have a bit of inline assembler in them. I mean, if you're abstracting the hardware and don't know how assembler works, you're probably not going to have a fun time anyway, right?
Yeah, but I think the idea is that if you're thinking about a special function register, everything runs off of memory mapped stuff, right? And so we already have the concept of memory. Why create a function to abstract the concept of trying to write to a register? Why don't we just use this concept of memory that we already have and continue to use this concept of memory? We need a way to identify and mark up something to be volatile, as the embedded world uses this term volatile. It's a useful term.
Well, in the abstract machine, we don't really have the concept of different memory being different, right? Like, it goes into memory somewhere. Even as Ben said earlier, putting something at a specific address is already kind of hard to do without getting into undefined behavior, right? I mean, if you're not doing it in a linker script, but that's kind of masochistic.
Placement new. Placement new it.
I think placement new does the trick, but you better be not too upset at what happens with the existing data there, I guess. I'm not sure. Yeah.
What about a lot of serial ports have the send and receive be the same address, and you get the received bytes if you read from it, and you send a byte if you write to it. So you basically have two pointers to two different, conceptually different things that have the same address.
No, you write an object. That's what Dan Sachs was doing. You write a single object that has send routines and receive routines, and this pointer is pointing to that location, and it's all nicely hidden from the caller. The caller just says that they want to, operate on these member functions. It's a really nice abstraction. It doesn't require any assembly language. It's really nice to do. It's just not legal.
Yeah, I'm not sure why. So a volatile pointer to an int or a volatile int, those make sense. I have a hard time thinking of when I would want to use a big class that has a bunch of different members and making that entire class instance volatile. I'm not saying I'd never come up with that, but I have a hard time.
The thing is, the data member of his class was just an int.
But that's the data member and not the object itself. So you wouldn't have a serial class, a serial port class where you declare it volatile serial class, my serial port. You would have a serial port that has a member that's a volatile int.
Well, he was creating the object in that place, right? He created the object in that place, and then he could just read and write from that object. And it was completely abstracted whether is that a data member, is it 6 data, it doesn't really matter. In practice, yeah, it was just he was sitting on a port. The object doesn't actually have any data members, right? And so it's this pointer is simply pointing to wherever the port was, and you would read and write.
But what if the port? Some chips make you write in 8-bit mode to the I/O port, and if you're taking the this pointer and essentially the compiler thinks you're writing to an int, and the hardware says, hey, you wrote in 32-bit mode, so I'm just going to ignore that. That happens on some chips too. This is where this kind of gets down into the weeds. Actually, I just realized this episode is totally scaring people away from using C++ on the We're doing the wrong thing, guys.
This whole show is scaring people away from using C++.
Maybe maybe it will do is it'll refocus Ben. Ben, instead of all this freestanding stuff, just fix this one problem so we can actually do memory mapped I/O without it being illegal.
I'm gonna let other people do the volatile paper, the big catch-all volatile paper one day. I'll stick with the tilting at windmills when it comes to exceptions and the like.
Yeah, well, that's you just mentioned exceptions. Well, I heard the word exceptions and my spidey sense started tingling. That's probably the biggest, syntactic thing that we can't use on at least the bare metal end of embedded for various reasons. But I guess that's maybe going to get fixed.
Boy, that would be so cool. Of course, people who've been listening to this show know I got very excited about when we talked about that. So maybe I shouldn't dominate this show talking about that. But I wouldn't mind listening to Ben or Michael or you, Odin, talking about, because you weren't on when we talked about it earlier. Have you looked at this proposal of static exceptions or herbceptions or whatever they're called? And what are your thoughts?
I think my name was on some version of it at like position 200 or something, and I probably didn't even deserve that. But the idea is to use the return path because modern processors are getting registers that are wide enough that you can store a lot in the return path without having to go out of registers. And so your return value, if people are familiar with boost outcome, this is basically compiler support for boost outcome or language support for boost outcome, where you have essentially, rather than just a return value, you have a variant of either the return value or the error that stopped it from coming into existence. And since we can do this within the language, we can actually potentially use compiler flags to discriminate between these two things. And it sounds like it's going to cost you because it sounds like more stuff, right? But on a modern processor, if you're not memory bound, you are crazy good at optimizing things, right? Almost everything is almost always memory bound. And since checking a flag that discriminates between a union in registers doesn't touch even cache, an outer order executing processor will be essentially always just as fast. But then you have all the advantages of it being deterministic and not needing all this bookkeeping and not needing some emergency buffer in case you run out of memory and blah, 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 which means that us guys with tiny chips can actually use them.
Yeah, I think my name is also somewhere in that paper. And the way I like to think of it is that I've already got a bunch of code that uses return values to, or in-out parameters to deal with their error conditions. And this is basically automating all of that work for me. I'm already comfortable with those costs. I'm already paying the costs for the little bit of extra code size and the checks right after functions run. So this is basically doing it for me, and that's wonderful because I am so tired of typing if status is fatal return.
The yeah, Michael, I didn't let you. Or is your name on the paper too, Michael?
No, I'm gonna say my name's not on the paper, so I'm actually the only non-biased opinion at the moment. So I think I should get some extra points. No,
Or just put everybody on so nobody can hate on it. Yeah.
No, it looks really exciting because it is this constant annoyance of trying to figure out how to deal with errors in a very clean way. And when you're especially we swap between a lot of different types of coding here. We're coding small things, big things, large servers, all kinds of stuff, and it feels like people taking things away from you, right? You get to the little embedded thing, and it's like, my error path sucks. It looks like C code suddenly. So this would be really nice.
I think just the idea that you could consistently use the same kind of error handling in all environments, because that's the beauty of exceptions, is that it used to be back when I was learning to code many thousands of years ago. You'd look at examples, and the examples would always be some little disclaimer saying, the error handling has been removed for clarity or something like that. And the real problem was that everybody had their own flavor of error handling, whatever framework you were in or whatever, And then when I started seeing people saying, well, I'm going to just use exceptions for error handling, we'll just clear it up. It was like, yeah, this is the way we should do it. And code should just use error handling. And then it doesn't matter what kind of error handling I use when I call your library, it just error, And then you get to embedded, where it's like, oh yeah, here's the situation where it really doesn't work as well. And that's really frustrating, because I like the idea of having a single way of doing error handling and make it universal. And then it breaks down at the very, very low end. And if we could figure out how to finesse it, which is, I think, what's really going on, we're making something that's just really a return code, but we're making it look like to the language, to the writer, as if it's a thrown exception. Wow, that just cleans up the programming model so much. Love it.
But it's not just a return code, as Odin was saying. It actually goes even further, because we can take advantage of the register layout and avoid the cache and get all sorts of optimizations out of it.
Yeah.
So it is. The title of the paper is Zero Cost Exceptions, but the promise is actually potentially negative cost.
A better return code than return codes.
Yeah, exactly. We'll see how that pans out. But
it's certainly a better exception than dynamic exceptions. So.
And it would potentially give us better interop. I mean, this is looking way into the future, so don't kill me if this doesn't end up happening. But it potentially gives us the option of better interop with other languages, because if you look at the way Swift does exceptions, or the way Rust does exceptions, or the way some of these other languages do exceptions, they're also multiplexing on the return code. And since we talk to each other via C, that would have to move too. But I've heard rumors that might not be over my dead body. Then we might be able to propagate Rust exceptions all the way into C++ code.
Yeah, there's talk of an ABI change to make that possible, so you can actually propagate
that would be awesome.
into C. Yeah.
Well, this is no fun. We're all agreeing.
Yeah, somebody say something I don't agree with.
Well, if you want your fighting words.
Oh, yeah, no, that.
Where is mine?
So my fighting words paper is basically saying, yeah, now we should make it to where you don't have to have dynamic exceptions and RTTI and all of that in the language. And there are people that may not like that.
Well, I hope that reflection at some point allows you to build your own RTTI, and so we can take it out of because it's kind of all or nothing at this point, right? It's up to the optimizer to figure out what needs RTTI and what doesn't, and that's pretty impossible for it to do. So you turn on the world or not, right? It'd be nice to be able to do very fine grade. Okay, I do want to know the name of this thing, and that's all I want to know.
Yeah, I like to think that if you take and if you get your time machine and you go to the future about 6 or 10 years and grit metaclasses from there, and then you throw them back to 1998, then or 94 or somewhere around there, then we probably wouldn't even have RTTI as a core language feature. You just build it on top of metaclasses as you need it. But time machine's broken and all that. So.
Well, you need metaclasses to build a time machine, obviously.
Metaclasses. Is there anything they can't do?
Nah.
Yeah, is this the new modules? Right, it solves whatever problem. Oh yeah, modules will solve that. Yeah. Metaclasses will solve that. We should talk a little bit about C++ and embedded, because this is something that Dan Sachs has raised. He said, in his opinion, for what data he had, it looked at one time as if use of C++ and embedded was going up. But he says we seem to have lost ground, and he believes his contention is part of the reason we've lost ground is because we keep talking about all these features coming out of the standards committee that are not really embed friendly, and embedded programmers aren't necessarily getting excited about some of the things that we're talking about. And so he says it's more of a perception thing. C++, because of things like const expr and things like that, is actually getting more and more embed friendly, but it's not portrayed that way, or at least not perceived that way. And so he feels like we're losing ground in the embed community. And as somebody who's running the embed conference, what are your thoughts on that?
Well, I think for one, we're not selling it very well, but I think there is.
I mean, we're not selling C++ very well.
We're not selling C++ very well, but I think there are legitimate critiques of C++. I think there are teams, and there are teams that I've come into. I've come into the company in consulting role and said, okay, you don't have any whiz-bang C++ guy. Maybe wait till you have one, or wait till the advice is more mainstream. I mean, there are things that will bite you, and there's not a lot of there's not just a book I can point at and say, hey, read that, and then nothing will bite you, right? Or the freestanding proposal, for example, would help a lot, because then you could say this is the part of the STL that won't bite, right? That's basically what freestanding is. That part doesn't bite you. The rest, maybe, maybe not. Read the manual. Problem is, if you read the manual, it still doesn't say, at least without the new freestanding proposal, it still doesn't say if it'll bite you or not. That's just not part of the manual of C++ yet. But I think there's an even more fundamental problem. Why is C++ awesome, right? C++ is awesome because it allows you to abstract things. It allows you to encapsulate expertise. It allows you to write something and write it in such a way that somebody else can use it without needing to understand it, right? But in embedded, we can't really use the same encapsulation rules. I can't even say it. Anyway, what if we need to share data? How do we synchronize that? Locks don't work with interrupt service routines very well, right? That's a lot of people are going to be using interrupt service routines because that's how we write code, at least on microcontrollers. That's why you pay more for a better microcontroller, because it's better interrupt vector control, right? So we can't use locks. The optimizer is also not good at optimizing away extra data. Extra code, it'll go to town on that. Extra data, well, we don't care because RAM's cheap, right? Except on microcontrollers.
Except for it's not.
There's a fundamental problem here. I can't just say, oh, you're not using data field X in class Y. I'll just optimize it away, because the size of that class and the layout is observable at compile time. You could write a metaprogram that decides things based on the size of that class, right? So the optimizer has a very, very hard time proving that not only can I remove that, but I can shrink everything down to still have contiguous memory, blah, blah, blah. So it doesn't, right? And so, somebody... the way it's done now, somebody takes somebody else's C code and says, oh, yeah, well, I'm not using this feature, so I'm just going to rip out that data, and I understand the code, right? That model only works when you understand the code. And in C, except for macros, which is, yeah, but okay, bracket that out. I understand the code, so I can go edit around in the code, even as sort of a normal run-of-the-mill programmer, right? But if I want to look into somebody's, C++ abstraction, I mean, we have powerful extractions, but there's a lot of semantics that give us that, which people need to learn, right? So you can't just go and edit library code in C++ the same way you can in C, right? So if the optimizer can't take it away and you can't take it away, then it's bloat, right? So until we have a good way of abstracting things that works on whatever the basic interface is that we're programming against on hard real time or microcontroller or memory constrained or whatever, that is as long as we don't have that basic interface, then 90% of the reason why we're awesome just doesn't translate to that domain, right?
Well, I think
so that's my opinion.
These are all the negative things. Come on, Odin. I think so negative. But I think those same things, right? The ability to abstract, the strong type system that allows us to know at compile time things are going to work in ways that we can't actually know in C. There are a lot of benefits to just the core language, and people get wrapped up in that this latest library feature or the standard this isn't going to work for me, or all these other things aren't going to work for me, and therefore I'm not going to look at the language. It is kind of a really it's almost like the detractor. But if you just looked at the core language and what it provides for you, it's a superior language because of the guarantees you're going to get about your code when it compiles. You know so many things about it that are going to work. Whereas with C, you're just like, I don't know. There's so many things I don't know at the moment on whether it's going to work or not. And I think if we spent more time just concentrating on the core language itself and what it does well, we can probably, evangelize more people over that they're using it. And I think a really good example is listening to Jason Turner when he's being interviewed by the Embedded FM group, right? Embedded FM is a podcast that's been around for a really long time. And it's just like people on two completely different planets talking to each other. And the reason is because the embedded world in general comes from C, has a concept and an idea of what C++ is, which is this bloated thing that happened in the 90s. It was actually very awful. And though some of us lived through it with horrible scars, but we came out and we believe in unicorns now, don't we, Odin? Unicorns are great.
Yes.
Yeah, unicorns. And if people came to the language without the baggage, they would see the benefits of it. And I think we're just not good about talking about what the benefits are of the language as is, right? Yep, sure, there's freestanding. There's all these other proposals and things around, but the language as it is right now is incredibly powerful and better than C.
Yeah, I agree on that. I'm just not good at selling it, apparently.
Could you, Michael, would you, given this opportunity, suppose you were talking to an embedded programmer using C, what would you show them about C++ that they would say that they might not be aware of what they could do, or how it would be more maintainable or more efficient or something?
Yeah, so in the CPP Now talk that I gave, I talked a little bit about this, how the ability to push domain-specific, the thing that actually gets companies paid money at the end of the day, business logic, things like that, pushing that up, pushing chip domain stuff down, it's very hard to do. You'll never look at a C base an embedded base where it's just like all this stuff is wrapped together. It's horrible, right? It's very hard to make nice, clean, layered systems. So you just kind of start with that, like, well, I have logic I can test on my laptop and know whether or not the business logic is just, the logic is good. That's a great place to start. But as you start looking at interfaces in C just fall apart. Here's an interface. It takes 4 ints. Each of those ints mean very special things. Okay, well, if I swap them when I call it, perhaps I just destroyed something, right? And sometimes those bugs are very subtle, and they're such that the testing environment's one where you don't really experience it. It gets experienced like first user who tries to turn the saw on, and now the saw has done something very bad, right? So I think strongly typed systems and showing elegant interfaces is usually a good way to someone who has experience with embedded, has been through all these war stories. They know that the integration of things and the calling functions with the wrong parameters just happens way too much. So I usually start with that, those two things, where we can show that business logic is getting pushed up, chip-specific stuff is getting pushed down. We have nice interfaces. Interfaces are meaningful when we call them. They can't be used wrong. Well, they could be used wrong, but you really know it.
It seems to me that among the arguments I could use, and one of them might be, if you use this, your code will be easier to understand, easier to maintain, better to separate into layers, all those things. That's often met with a certain amount of skepticism because, first of all, maybe it's not true. And it's a little hard to know for certain. That's, if I could make the argument, oh, it'll make your code 5% faster, I don't care what I have to do. I'll walk through fire for 5% faster. And I think that's one of the problems is that if you're really going to appeal, you're going to have to show how this stuff that would be done at runtime is now being handled by the compiler. And that will get people's attention. But just saying, you're going to have a better interface, I just think you're going to met with skepticism, because they're going to say, well, yeah, some things might be easier, but I have to learn C++ now, and I know that's impossible.
But I think there are two answers to that. Our responses. The first response is anybody who has done a project knows that the problems are you put the thing together very quickly and it takes you forever to integrate it and debug it properly. For embedded systems, it's really hard. And knowing that by construction, the compiler told you you constructed the thing right is just huge leaps ahead. The other is,
but the
this
problem
seems
is
ironic.
when you tell me this, my first impression as a, and I'm not really this, but as a C programmer who's doing embedded, my first thing is, I'm not going to believe your compiler.
Well, okay, so in that,
you see what I mean? I mean, I have a certain skepticism that it can do it, and a certain skepticism that it will do it.
So that's just the type system, right? So that's easy. But the other is the hard part. The other is, if I tell you that the compiler is going to optimize things and make stuff go away, you are now scared and running to the hills, because generally, most embedded programmers will use O0 to compile. They want to write C code and have this translation in their mind that C code somehow becomes this exact assembly. They know what the machine is going to do without the compiler messing with it or mucking with it along the way. And as soon as the compiler starts mucking with it, then the questions are, well, how much did it muck with it? Did it muck with it too much? What did I lose? How do I know if I don't change this other thing that all my timing constraints now change to something else? Which, funny enough, right? They still have that problem in C, but it's a perception. It's largely a perception problem. So having the compiler do more work for you and optimizing things away is actually, at least in my experience, has been the biggest battle of trying to get people on board. It's like, you can't depend upon that anyhow. You have to write tests. You have to write performance tests. You have to write functional tests. You have to test things to know that it's going to actually work properly. That's what you have to do.
And to be able to write good unit tests, you need a good interface that's mockable, which is also hard to do in C. I mean, if you're doing like a split backend to mock it, which basically means you have, some header file and then you have some other CPP file or C file in that case, which you're going to swap out with your mocks, so that the header provides the interface and then you swap out the backend to be able to mock it. Well, if you're not turning on link time optimization, the compiler is not going to be able to inline those calls. And if you are turning on link time optimization, you better sure as hell know what the rules of optimization are. Otherwise, it's going to screw with all your code. So zero cost mocking in C is very hard to do. You can play around with macros, and that's not a sharp corner, right? But zero cost mocking in C is very hard to do. In C++, you have some interface. Maybe you have some traits class, specialize a traits class with your mocked out thing. Default is talk to hardware, right? It's easy and it costs you nothing.
If you build it into your initial design, it's pretty easy, but it does require designing for it. And I've
Sounds
definitely
like you
run
have
into
legacy code.
I've had plenty of issues where, man, I could put a test seam here, but that's going to be a big syntactic pain point to put a test seam there, or it's going to be a performance hit. So I've run into those kind of issues before.
But it could have been designed in, you're saying? Had it been designed in, there could be a test seam already there.
Potentially, but yeah, part of the designing in would be, well, maybe I put some nasty macro thing here, maybe I put it into a separate translation unit, and make sure that the production code and the test code include the right headers depending upon which mode they're in, and there are some nasty things that can go on there. If you're just talking to special function registers, that may not be too bad, but if you're mocking out something that is at a higher level, it starts to get nasty.
So, and just on that, right? The special function register. You see this all the time, or as I do. Maybe I'm just looking at a lot of bad code. they leak up. So pretty soon you have business logic that's like accessing the special function register to do whatever it wants to do, toggling an LED on. I mean, it could be as simple as that, right? And why? Well, because calling through layers is a penalty that I don't want to take. Well, it wouldn't be a penalty if you use an abstraction that was zero cost, right? One that would compile away. It wouldn't cost you anything to write this in such a way where it would just disappear. But there's not a way to do that in C. So instead, I'm just going to turn the LED on.
So, Ben, what do you think about what Michael said about what it is that embedded C programmers push back on? Have you fought this language war on the embedded level?
I have fought it a lot on the kernel level. So as I've been pitching my papers to some of the mailing lists, it's like there's the NT dev list. So that's the kernel mailing list for Windows, basically. And so I say, hey, everyone, look at this paper. First response to that paper, why aren't you using C? And, you know, nothing productive gets done there. So it's even difficult. I imagine same thing happened on a lot of the embedded mailing lists, to where it's like you say, hey, there's this thing about C++ that I'd like to discuss, and then immediately it goes completely off topic into why are you even using C++? So that's kind of the hole that we have to dig ourselves out of on the C++ front in some of these environments, is even getting past that first hurdle of can we even talk about it and not have the meta conversation about why are we using C++.
One thing that we had at our conference, which actually comes back to what John was talking about, you know, give me speed, give me something I can't achieve in C. You know, we had you know, actually quite a few people that came from a C background, and this was their first, you know, C++ interaction really. And you know, one of them was completely convinced that you could do anything in C, right? I was talking to him sort of, you know, before some of the talks. And then there was a talk by Emil Freysk, if you want to Google it, from the EMO conference. And it was about a sort of an alternative scheduler, right? And the scheduler leveraged the interrupt service routine hardware in the chip to do task switching in like 7 or 8 instructions, essentially like 2 instructions more than a function call, right? So just insanely fast task switching and insanely fast locking and deterministic locking. And the thing about it that you couldn't do in C was he was using template metaprogramming to essentially, you give it a list of the priorities of all your tasks, and you give it a list of all the resources that you have that are shared between these tasks and who is allowed to access them. And the metaprogram would figure out, okay, what's the highest priority level that anyone's going to access this specific resource? And if you are that priority level, you don't have to lock, because who's going to interrupt you, right? And in C, you'd have to program this by hand. So somebody would have to, you know, change the priority on something because they weren't meeting timer requirements, and then they'd have to go and find all the resources that have to have, you know, locking changes and blah, 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 and it'd just be completely brittle. And you break everything every time you change anything, or every time you added a new shared resource or whatever, you break the world. But using this, you know, template metaprogram data structure, which is presented to the user as just a list of your, you know, you pass in a list of your shared resources, you pass in a list of your tasks, you give each one of them priority. You know, it's kind of like using standard vector, which is, you know, a template, but it's still easy to use, right? So you can't do that in C, right? I mean, this is efficient, you know, very, very efficient, much more efficient than you would be able to write in C, because there's an ugliness level, right? You can write everything in assembler if you want to, right? That's going to be so brittle and ugly, you're never going to finish that project, right? And there's an efficiency level in C where you could say, okay, you can write that in C, but it's going to be so brittle and ugly, you're never going to finish that project. Whereas in C++, you can wrap that brittle and ugliness to where the user gets an interface that's not brittle or ugly, right? You know, there is some 2 Dutch students who did a paper recently. I'm not sure if it's been published anywhere yet. I read it. It was comparing our quasi-register abstractions to hand-coded assembler, and then comparing that to the C code, which the chip manufacturer shipped with the chip, right? And sadly, my super efficient TMP optimized register interface was, about twice, half as performant as they were able to do in these specific tests with hand-coded assembler, right? But at the same time, the chip manufacturer's C stuff was about 10x slower than they could do in hand-coded assembler. So C++ still 5x faster, and it's right. I have to go into about 10 places in my code because they basically found a faster way to do it in assembler than I was aware of. But I can go into those 10 places in my code, and suddenly, because this is an abstraction or 3,000 kinds of chips, I have to fix 10 places in my code, and then it's twice as fast, right? You can't do that in C because C doesn't have a built-in code generator. C++ does, right?
So for those people who showed up at the EMBO conference from the C world, you said that was their first experience to C++. What's the situation? Are they converted? Are they coming back to EMBO to learn more about C++? What's the situation?
I think the vast majority of them are coming back. Those non-converted probably didn't talk to me. I think we sold everybody on. This isn't the first year we did the conference. I think there's enough diehards that come every year at this point that I don't have to evangelize everybody. The rest of the people do. But so I didn't talk to all the people that were using C. But there are people that are coming from very sort of C companies, right? Some of the German like industrial automation or automotive or whatever companies where they're using C. Why would you use anything besides C? And then another good selling argument is if you tell a C programmer just take your code and put it in a C++ compiler, then it will be a lot less efficient. Why? Because there's a lot of compiler flags that are on by default on a C++ compiler and off by default on a C compiler, right? Like canary objects. I have an array. At the end of the array, it'll put what's called a canary object, which basically just sits there with a magic number in it to see if you rip past the end of the array, right? A lot of GCC, ARM, EABI, blah, blah, blah for microcontrollers has canary objects on by default for some reason, right? So C++ can put all those in there. You have a little more safety, but it gobbled up a little stack space, right? Whereas in C, you can turn that on in C, and then you get that, right? So the naive comparison of I just compiled this with default settings in C and I compiled this in default settings with C++ is not an apples to apples comparison, right? You turn off those 10, 15, 20 flags that are on in the C++ compiler. A lot of people even leave RTTI on and leave exceptions on, and it gobbled up all my RAM, this terrible C++. But yeah, turn that off, right? So if you turn all that off and just run your C code on a C++ compiler with truly the same settings, right? Then C++ code, for the most part, is actually going to be more performant and smaller because of the stricter aliasing rules, because there's a few more things that are undefined behavior in C++. The optimizer has a little more room to do its thing. Maybe you did write C that depended on that thing that's undefined behavior in C++, or depended on, I have some struct and I have an int, and the pointer, it just supposed to be cast the void, so they're the same thing, and then they're aliasing each other and blah, blah. No. If you write code like that, okay, keep using C. We don't want you. No. It's brittle anyway, right? If you can write that code in a way that's type safe, and when you do, then it's also C++ code. And so yeah, if you tell them that and then actually show them that, there are some blog posts along these lines. Then you have a lot of people converted already because they can still write the exact same code, right? If they're running the team's infrastructure, they don't even have to tell the team that it's a C++ compiler. They probably should, but in theory, it'll still work. But then you can start using const expert, right? Or, you can start using function overloading or whatever else you like at C++. You don't have to use it all, right? You just have to, switch to the C++ compiler. Will cost you time, like a day of figuring out what compiler flags and whatnot. Or, depending on your chip vendor, a month of fighting it. I loved your talk, by the way, Michael.
Thank you.
But if you have a chip vendor that's not completely against you, then it'll be a day or two of playing around, and you can get your same code to work on a C++ compiler, and then just pick and choose what you want to use. I mean, don't use virtual functions on a microcontroller, but you don't have to. Nobody's forcing you. I mean,
right. So I think one of the things that I find interesting about this whole discussion of embedded and C versus C++, as if it's a battle, people who write C++ on embedded devices were also C programmers. Like all of us are probably just as proficient writing C as the most proficient C embedded developers are. It's the language we have to drop down to in order to get our startup code and a bunch of other stuff to work, right? So we probably, all of us had done that for some period of time. It's a place where we're comfortable, just as comfortable as we are typically in C++. But what we see is that the tools in C++ provide something that the tools in C don't. So we spend a little bit more effort so that overall the project has better quality. It's typically done in less time. That's why we spend time doing it. We write plenty of projects in C because we sometimes don't have a choice. It's a 4K processor with a bunch of restrictions. And so we're not going to spend any time on that. But where it makes sense, which is most of the cases, we spend a little bit extra time trying to get the processor and the compilers to support one another, because we know that we're going to end up with better quality and we're going to use fewer resources by the end of the project. And the customer is going to be happier, or we're going to have fewer bugs coming back. It's just kind of this, for me, it's a complete business equation. I stick the things in, I realize that it's better business for me to use this language than it is for that language. And it's not, some religious war at all. It's better business for me.
All right, so there's a couple of kind of linked questions I want to ask. It's in our notes for the show. It says, why should non-embedded devs care? So should they care, and why should they care? Why are people who are not in embedded, other than hoping that Michael's going to go off on some tirade or something like that, why are they watching the show? Why do they care about what's actually happening in embedded? How does this affect the non-embedded world? Any of the stuff that we're talking about?
Maybe they're also writing code for GPUs or kernels or something like that, and those all have very similar restrictions. That's one reason.
Okay.
And future things. I mean, basically the freestanding is, this is something that doesn't, secretly share things under the hood. I mean, that's not exact, but that's very close to what this freestanding subset is. And I don't care if you're looking years into the future where we're programming, I don't know, organic processors that have a completely different memory model or whatever. As soon as I am explicitly passing all of the state in through some interface, then I understand that's my job as a programmer to synchronize that or to make sure that's on the right bus or whatever the other constraints of my environment are. Whereas if it's secretly being used under the hood, even though I don't see it anywhere, that applies to a lot more than just microcontrollers. But the argument that I would bring is, you use embedded systems. You don't want your stuff to crash all the time? Fix that. I mean, you don't want to like unplug all your stuff and plug it back in all day? Give us the tools, man.
All right. So that leads me directly into the second question, which may be a softball question to you guys, but what is it that you want the committee to give to you guys? We've mentioned freestanding. We've mentioned throwing out volatile, or maybe not throwing out volatile. What is it? Give me the top three things that if you could have these through the committee, your embedded programming life would be a better life.
So my 2 papers plus lightweight exceptions. That's what I want.
All right. So your 3 papers are freestanding.
So there's a library freestanding proposal that's adding stuff to the standard. That's adding stuff to the freestanding subset that is suitable for systems without an OS. My second proposal is removing a bunch or making a bunch of stuff not required that doesn't really make sense in embedded and kernel environment. So it means that exceptions and RTTI and thread local storage, none of those would be required. And then there's the lightweight exception stuff, which we've talked about.
Okay.
That one's not my paper. That one's hers.
Yeah. And the you did kind of say it, and I assume most of the people in the audience know what freestanding. But again, the idea is that the standard does document and says that you may be running an environment with no operating system. And in an environment with no operating system, some things are not available. And you're trying to widen that and say more and more things should be available because there is, in fact, a way of delivering this functionality without an underlying OS. Did I capture that right?
Sort of. So I am trying to make freestanding match that mission statement. Right now, it has the wrong set of library things. Mostly it's got too little, but there are some things that are documented that are in freestanding that don't make a lot of sense there. And then on the language side, there's a lot of language features right now that don't really make sense on an OS-less system. Okay. And so that's what those two papers are trying to correct.
And I don't know if your paper handles this or not, but there seems to be this constant coupling through headers of things that just don't make any sense. Like you try to grab, a header file to include something that would work perfectly well in your non-OS environment, and it yanks in like
IO streams.
Like IO streams.
The iterator header pulls in IO streams.
Yeah, there's a perfect example right there.
The string view header pulls in std accept, and std accept generally depends upon string. So yes, I try to address that, and it's painful. It's like these things should work, but they don't. The compiler's just yelling at me.
We're back to spaghetti code, huh? All right, Michael, you are ISO king for the day. What are your 3 wishes?
Ooh. Wow.
You want Odin to go first?
You'll be sorry.
No, not that. I do want the what? How are we saying this?
Herbceptions.
That's what I want.
Static exceptions.
No, static exceptions. I really like the idea, and it would clean up so much. It's pretty high on my list. I personally would love a lot of things to be decoupled. That just when I'm pulling in a header file, I get so much crud that I suddenly can't use things anymore. It's just nuts. So that would be nice. I'm going to admit I haven't read through all of Ben's papers. I've glanced through them multiple times. Sorry, Ben.
I forgive you.
I totally suspect there's some really good things inside there.
All right, Odin. Can you limit it to 3?
Yeah. Well, okay. I think static exceptions and freestanding are definitely top of my list because they're somewhat realistic. I think coroutines will eventually play a very large role in embedded because we do a lot of event-based stuff. But the problem with the current Gore routines is going to need a lot of unpacking. Do you mind if we go a little bit long?
Actually, I would rather have a whole separate episode on that one. I mean, we can invite you back because I've been talking to a lot of people about this. Maybe not that much, not that many people, but I've been talking an awful lot to a small number of people who have some real serious concerns about Gore routines. So I don't want to, we're pretty much out of time now. It's a bad time to start this topic.
I want coroutines.
I want the coroutine programming model, and I think there's some implementation things that I would love to see improved. But yes, I'd like the idea of the coroutines programming model very much.
And in Gore's defense, I would like to note, like for some context here, in Gore's defense, I think to be able to properly abstract coroutines with C++ tools, as in small composable pieces of magic rather than one giant ball of magic, you need to move a lot of stuff, and that's way too much for one guy. So I'm definitely, don't want to take away from my admiration for what Gore has done in that field, even though if I disagree with his coroutines.
I've heard people who are critical of the proposal, but I've never heard anybody say that Gore isn't a very intelligent individual. He's very smart, and he knows what he's doing. There are people who aren't crazy about this individual proposal, but nobody's saying that Gore is lacking in capability. I don't think that's on the
an effort. I mean, there's
So instead of like new features, John, and all that stuff, really my number one thing would be if we could really just take care of this memory mapped IO and how we utilize the word volatile and stuff, so that there's just like, we all know what it's going to do. And I think we all know in the sense, like, we keep doing the same thing because compiler vendors so far haven't broken what we ask compiler to do. But if it was just written down as this is what it is going to do, we would all just be comfortable with that, right?
And I guarantee you the compiler writers want that too. The
compiler
writers want that too. They want to be able to say, because they want to do optimizations right up to the line. And if that line's not defined, that's really hard for them, but it's hard for you as programmers to know, well, I want to code right up to the, I want to code from the other side up to the line, and they want to optimize up to the line. And if that line is fuzzy, it's not good for anybody.
But I think the language is so powerful as it is, the core bits of the language, that if we could remove some of the things that are the big uncertainties, and, at the end of the day, mapping addresses to something that we can use constantly, because that's the entire world of the embedded, that's huge. But the rest of it, I don't know, I'm happy with the language.
All right, what a great place to stop. The first person to ever wish anybody safe coding on this show was Michael, and so you want to lead us in wishing that for everyone?
Absolutely. Safe coding, everyone.
Safe coding.
Safe coding.